Have you ever wondered what actually happened within the exact second you hit your computer's power button and the moment your Linux desktop or login prompt appears? To us, it looked like magic. A quick motherboard logo, a few lines of white scrolling text, and suddenly you're looking at your desktop. But under the hood, your computer executed thousands of low-level instructions in a matter of seconds. Today, we're breaking down the Linux booting process, from firmware check and bootloader to kernel initialization and use space target. The boot process can be broken down into four main stages: system startup, bootloader, kernel stage, and init process. It all begins at the hardware level. When you turn on your machine, your CPU has no idea what operating system you have installed. It starts by executing code built directly onto your motherboard firmware, either a traditional BIOS or modern UEFI. In older BIOS-based systems, the BIOS run a POS, which means power on self-test. Check your RAM, storage drive, and peripherals. Once checked, the BIOS search for bootable device, like your SSD or USB drive. On a hard disk, it looks for the master boot record, MBR, which is a tiny 512-byte sector at the very beginning of the drive, containing the first stage bootloader and partition table. On the other hand, in modern UEFI systems, instead of reading raw 512-byte disk sector, UEFI understands file system natively, and it executes UEFI application file directly, like .EFI binaries. In fact, the Linux kernel can even be built with a EFI boot sub, allowing UEFI firmware to boot the kernel directly without needing a bootloader at all. Most of the time, your system passes control to a bootloader. The bootloader job is to prepare the system memory, load the compressed Linux kernel image into RAM, and then hand over complete control to the kernel. If you're running a standard Linux distro, your bootloader is likely GRUB2, which stands for GNU Ground Unified Bootloader. In BIOS setup, GRUB works in stages. There is Stage 1, Stage 1.5, and Stage 2. In Stage 1, GRUB search and load Stage 1.5. which is stored inside the 512-byte master boot record which we talked about before. Then Stage 1.5 read the primary file system and pass to Stage 2. Stage 2 then load configuration files and present the interactive boot menu you see on startup where you choose your boot entry. While GRUB is the default of many distros, Linux offers plenty of alternative bootloader depending on your use case. There is systemd-boot, a lightweight minimal configuration bootloader designed strictly for UEFI systems. There is SysLinux, which is commonly used for lightweight live USB and install CD. There is Refined, a flexible boot manager for dual booting UEFI system, and there is finally DAS U-Boot, which is a standard bootloader used in embedded system and single board computer, like for example Raspberry Pis. Once you pick an option from your bootloader menu, it will load two critical items into RAM: the compressed kernel image, often named vmlinuz, and an initial RAM disk image called initramfs. Now we enter the kernel stage. The kernel file loading into memory isn't executable yet. It's actually an archive that decompresses itself in RAM and initializes basic CPU setup and memory management. Next, it executes a function called start kernel. This is where the core of the operating system comes alive. It initializes CPU architecture, interrupt handling, and the system bus. Then mount the initramfs into memory. But why do we need initramfs? Think of it as a lightweight temporary root file system stored in RAM. Your real root file system might live on an encrypted drive, an LVM volume, or a software RAID array. The kernel doesn't include driver for every complex storage arrangement built in to keep its size small. Instead, tools like Dracat generate an initramfs image containing the essential driver and scripts needed to find and mount your actual root drive. It uses udev to detect hardware node, mount your real drive, calls a function named pivotroot to swap the temporary RAM file system for your real drive, and frees up memory. Finally, the kernel calls kernel thread to spawn the very first user space program, the init process, and hands management over to it. At this stage, the init process comes in. It always runs as process ID 1, the parent of all other user processes. Historically, Linux used SysVinit. SysV relies on numbered run levels, 0 through 5, controlled by etc inittab and shell scripts inside etcrc.d. Run level 3 represents multi-user clean mode, while run level 5 represents multi-user without GUI. But most modern distros use systemd instead. Rather than running shell script sequentially, systemd uses declarative target files and executes service in parallel for much faster boot times. As speed 1 takeover, it completes several final setup steps. For example, it sets the hostname, it sets up virtual file system, it applies kernel trick, check and mounts drive specified in fs tab, and loads additional kernel module if necessary. Once the init system brings up all requested target services, you reach the final step, user authorization. On server or minimal install, the system boots into a multi-user target and presents a TTY text terminal prompt asking for your login credential. On desktop Linux, instead, the system boots into graphical target and launches a display manager, such as GDM, LightDM, or SDDM. The display manager initiates your display server, Xorg or Wayland, and presents a graphical login screen. Once you type your password, your desktop environment, like GNOME, IDE, or a Talent Window Manager, loads and your system is fully ready to use. The Linux boot up sequence is a remarkable piece of engineering. It transitions seamless control across multiple handoffs. What makes Linux so unique is how modular every step is. You can swap BIOS for UEFI, GRUB for systemd boot, or SysVinit for systemd, giving you full control over how your operating system wakes up. If you enjoyed this breakdown or learned something new, consider leaving a like and dropping a comment down below. That's all for today. Magrid out.